Okay, let's just get started. This last lecture, yay. We're going to just go over some things very briefly. You've got these already, but I just want to, go over to refresh your mind. And then we're going to go and look at some past exams, and I'm basically going to tell you what you should know and what you don't need to know, because on those past exams there are some questions that you may see that you may not think that you have done, so I'm going to say which ones you don't need to know, okay? Okay, so let's, where am I? Okay. So remember we started at the Drude model, the very sort of classical way, and so you should know about Drude model, and you don't need to do any derivations in the exam, okay? No derivations this year. Like previous years, don't think you needed to do derivation, but you do need to know about the equations and the concepts behind them. You need to know about the Hall effect. Clearly, that's a very important part here, and what gives you a positive and negative Hall coefficient. You need to know a little bit about the thermal conductivity of the Drude model. This is what you expected to know, okay? I'm not telling you this is what's going to be on the exam, so don't get your hopes up. You should know about the Wiedemann-Franz law. You should know about the Lorentz number. You should know about the free electron gas, and all about these Fermi quantities, the Fermi wave vector, Fermi energy, Fermi temperature, Fermi velocity, and have some idea about the order of magnitude of these things. Yes?
Sorry, I have a quick question. Where you've got the lines for the word derive,
yes.
I'm assuming that's stuff we don't need to do.
Yes. Let me qualify that. The word derive is what you don't need to do. You will still need to be able to discuss, for example, the Drude model, but you don't need to derive any equations. Yeah, you'll should know a little bit about the temperature dependence of the specific heat. You should be able to, know where the Drude model is good. Is that hat because it's the last lecture? Good idea. Yeah, so you should know and be able to compare a little bit Drude and Sommerfeld model, how they are different, and where there are advantages and disadvantages. As I mentioned before, you should know about those Fermi quantities. What is the expression for the density of states and the Fermi-Dirac distribution function? Okay, now, I'll get to that a bit later on, but there will be no formula sheet this year, so you really don't need to know off the top of your head any equations. You don't need to actually, be able to recall those, because they will be there for your use, so you mainly need to know how to use them. There will be this year, yeah. This is one of the difference to last year's. So we are reintroducing the formula sheet that was taken away some years ago. I'll get to that in a little bit. Okay. So then we did some things on crystals. Okay, you should know how to define and what is the Bravais lattice, primitive cell, conventional cell, Wigner-Seitz cell, a basis, and the Miller indices and how to get them. You should be familiar with the reciprocal lattice vector. So if you are given a direct lattice, ABC vectors, you should know how to apply those equations. Remember the B equals 2 pi on whatever B cross C over A dot B cross C. They will be on the formula sheet anyway, but you should know how to work those kind of things out. And I think, like from the assignment one, the feedback that I got was, I think it was more the normal students. They had sort of this linear, just a one-dimensional cell, and some of them got a little bit mixed up with that. So just make sure that, you are good with reciprocal space. Okay, we did then packing fractions with various crystal structures, and we spoke about which one has the highest packing fraction. We did some derived I don't know if we derived it, but we talked about the structure factor, right? And how that's a mathematical expression that describes how waves are scattered in a crystal to give off the various diffracted beams, which are then used, to interpret about atomic positions in the crystal. So the structure factor is used to derive the atomic structure of crystals. Okay, and yeah, you should have some idea of how large typical lattice spacings are, like say 3 angstroms up to 5 angstroms, that kind of order of magnitude. And remember, we talked about the 5 different types of bonding in the materials. You should know what they are off the top of your head. Not too hard. And then we did Bloch's theorem. It defined Bloch's theorem. Maybe I should have a cross there. You don't need to write down the equation for Bloch's theorem, but it'll be in the formula sheet anyway, but you should be prepared, perhaps you should be able to discuss aspects of Bloch's theorem. You know that it's a plane wave multiplied by a function that has a periodicity of the crystal. Okay, the velocity of an electron. Remember, we defined the group velocity. We had the band structure, and the group velocity went over to 0 at the band edges when we had the nearly free electron-like model. And also in the tight binding, you get the curving over of the bands, and the group velocity is just the gradient of the energy versus K curve. Yes, you will need to, you would be expected to know about, the nearly free electron approximation, the free electron approximation, and, aspects also of the tight binding approach that we also used. Sketch the energy bands in a one-dimensional, okay, yep. This here is relating to, remember when we had, we did reduced space and we did extended space for our band structures. Remember the band structure went to the first Brillouin zone, then it was folded in. So that's called the reduced space. The repeated zone is where it repeats at all the K points. So you should have those pictures in your head. Yeah, and you should know that the free electron approximation has no gaps at the boundaries. It's a perfectly free electron. It doesn't feel any crystal potential. And then when we introduced the nearly free electron potential, we treated it as a perturbation, and we assumed that the electrons were experiencing a very weak potential. And that's how we derived that these band gaps opened up that were equal to twice the value of the perturbing potential. Remember, we had the band gaps here opening up at the Brillouin zone boundaries, and they were equal to 2 times V. Okay? Sketch how the energy levels change as atoms condense to form a crystal. Remember, we had those pictures. You have the discrete energy levels for atoms. When you bring them closer together, we get the broadening of the bands and the hybridization of the states to form electronic bands when you get into the bulk. I think there was a picture. I don't know which lecture it was in, but that's what it's talking about there. Atomic level and bringing the lattice constant smaller and smaller and seeing how those energy levels broaden and change. And we talked at the same time about metal insulator transition. Remember we had metal insulator or insulator metal. I think at that point we had a band gap. And as we reduced the lattice constant, the valence band and conduction bands got smaller and smaller. And at some point they touched, there was no band gap, and so that is where we had the metal insulator transition. So everything is in your lecture notes, okay? Everything's in your lecture notes, everything, or the assignment, or the quizzes. Nothing extra, nothing else. Okay, what's this about? Yes, okay, metals, semiconductors, and insulators. You will be expected to know, what's the difference between metal, semiconductor, insulator? What are their properties? What is a Hall? Again, why can the Hall coefficient change? Because it can actually detect not just the electron or the carrier density, but it can detect the sign. So it can detect the presence of holes as carriers as well as electrons. Okay, lattice vibrations. We did the one-dimensional chain with just one species, and then we got just the optical branch, and then we introduced 2 different atoms per cell, and we saw that we got not only the acoustic but the optical branch above it. So you should need to know, what those bands look like, and what's the difference between having just one atom in the unit cell, you just get the acoustic branch, and 2 atoms, you get both the acoustic and the optical branches. Okay, what do they look like? Okay, this is exactly what I just spoke about. We just did a one-dimensional chain, and with 2 different atoms in the unit cell. Okay, so it's all coming back to you now, this marathon. Okay, then semiconductors. Yeah, you'll need to know a little bit how the conductivity changes with increasing temperature, and conversely the resistance. Definition, what is the difference between intrinsic and extrinsic semiconductors, and degenerate semiconductor. Now, we spoke about all of that. Remember, the degenerate one was when you packed so many carriers into the material that it becomes metallic-like. That would be sufficient if you were asked what is a degenerate semiconductor. Under this assumption, show that they can be potentialized halfway between. You don't need to show anything. As I said, you don't need to derive things here. Yes, doping, you'll be expected to know what doping is and how doping can be used to change the conductivity of your semiconductor. Right, remember, we had the silicon, and if you introduce phosphor, you get this extra electron. So it'll become, you get extra electron carriers in your system, and it will be located sort of up in the conduction band or near the conduction band. That state associated with the phosphor, that extra electron. And conversely, for the whole doping, yeah, we may have doped with aluminium, I think. And remember, aluminium only has 3 electrons, but our host has 4 electrons. So by doping with aluminium on the silicon site, we introduced a hole in the valence band. So remember, you've got your valence band. The aluminium dopant will introduce a state that's empty just above the valence band maximum, very close, just some MeVs above it. And that allows electrons from the valence band to jump up into that empty state, and that's the way you get your hole, okay, in the valence band. What is the difference between direct and indirect band gap? Yeah, we talked about that. Remember, the direct band gap was when the valence band maximum is exactly at the same K point as the conduction band minimum, whereas indirect is where they are at different K points. What is the law of mass action? Yeah, you should know what that is. You don't need to write down the equation. It'll be in the formula sheet, but you should know how to use it and kind of be familiar with what it looks like. Yeah, no deriving. You don't need to derive anything. Yeah, magnetism. We spoke a bit about diamagnetism and paramagnetism. There were 2 types of paramagnetism. Remember, one that was related to the core electrons, and the Pauli paramagnetism, which was related to the free electrons. So there's 2 types of Pauli paramagnetism to consider. And then we showed Curie's law, and so it had the form, the susceptibility is equal to a constant, which is a Curie's constant over T. Yeah, you don't need to derive it, but you should be familiar with it. And, okay, what is the origin of magnetic order in the solids? Remember, that was like ferromagnetism or antiferromagnetism. We had that exchange interaction between the spins. So that's what the mechanism is of achieving a magnetic domain in your crystal, the exchange interaction. And the susceptibility is different when the spins are aligned, because there's an equation there that relates the susceptibility, I think, to the derivative of magnetism with respect to I forget. But the magnetism will be different if you've got spins up like that. And for ferromagnetism, you'll get a substantial magnetization M. For antiferromagnetism, you get 0, right? And for, what is this other one? Ferromagnetism, you'll get some smaller value of M. We talked about the Hund's rules, so you should be familiar with those. You should know what a Heisenberg Hamiltonian is and an Ising model, sort of in qualitative terms, descriptive terms. You won't need to use them. You won't need to write down their equation. Let us see. That's about it. You know, we did have some sort of research kind of talks. We did do a bit about DFT. You know, you could know what DFT is. You don't need to know any equations for it. Is that all? I can't remember. This is all that I've prepared in any case. So this is designed just to sort of bring your mind. I know it's not until the 20th. I think your exam's not until the 20th, but it's always good to start thinking about it. Okay, so now on the overhead, I want to talk a little bit about the exam. Let's see. So, you know, as you know, it's worth 75%, I think, which is quite a lot, right? It's just the way it has been. Doesn't mean it's a good way, but that's the way it has been over the years. So, yeah, this year there will be a formula sheet. I don't want you to think, oh my God, there's going to be so many quantitative calculations involved. There will only be a couple, okay? The style will remain rather similar to previous years, as I'll explain later. So that's the main thing. You'll get to see a formula sheet. Yeah, I'll go through the exams shortly to show you which questions you don't need to know about, because there are some differences in the material to previous years. Yeah, I think you don't have access to papers 2015, 16 and 17. Is that correct? Yeah. I think the decision was made by the coordinator for some reason to keep those not available to students. I just want to say that those exams are very similar in format and style to the ones that you can see. I just want to let you know that. So don't worry that these 2015, 2016, 2017 are really different. They're not. I think it's because, you know, we had a new coordinator, new system, and, you know, a new marking scheme in that we are not allowed to standardize. You get what you get nowadays, okay? Yeah, I don't know if you can see exams before 28, but if you look at exams before 28, they are really quite different. So you don't actually need to look at those at all. They are, yeah, completely different sort of content. So don't worry about that. Probably you've seen on Canvas that there will be a tutor for you in Slade at 4 p.m. On Wednesday, the 14th, and again at 4 p.m. in room 4003 in the Sydney Narrow Hub. You know, he'll be there to answer questions that you have. And so please feel free to go along there if you have any questions. All of the solutions to quiz 3 and assignment 1 will be put up on Canvas as soon as possible, probably today. And I just want to emphasize, if you have any questions at all about the exam or other questions, just please email me anytime, or on Piazza. I should be, if I'm not in person, I should be in email able to answer. Okay, so this I think you've seen already on Canvas, maybe in a slightly different format to what's on Canvas. So it looks basically like that. You know, you can see you're starting off with the Drude. Here you've got the, what is it? God, the Hall effect. That's what I'm trying to think about. So you've got the equations for the Hall effect. You have got definition of the Fermi quantities here, the density of states, and these other equations that look familiar to you. Atomic packing, so if you're asked to determine that for a different structure that you've never seen before, you will remember how it's defined. And here we have the familiar reciprocal lattice vectors. And over here a bit more you have, remember from the scattering, the structure factor and the interplanar spacing and the lattice constant up here that you've used before in your assignments, I think, yes, assignments. And what else have you got here? You have got some information. Remember the equations for the phonon dispersion curves here, the frequency, remember? And there you have got the expression for the phonons here, the energy of the phonons. And what else? Okay, you've got here the law of mass action. You recall that one. And remember we had an expression to determine the position of the Fermi, or the chemical potential, we called it, in a semiconductor in the band gap. Here, remember this one here, it was dependent on the band gap and the temperature. We have some standard equations for magnetism and the various kinds of susceptibility. So all of that, yeah, you can expect to see at the end of your exam. Okay, so let's have a look at these sheets. I'll just blow it up a little bit. So this is from 2014, which is the earliest, the most recent one I think that you got access to. So let's go through it. Okay, the first question is about Drude and explaining the Wiedemann-Franz law. The tick means that you would be able to do that one. You would know about that. And, so a tick means you should know it. A cross means you don't need to know it, okay? So these ones you don't need to know. Why? Well, we talked about the Fermi wavelength of metals and so on, but we never talked about the Fermi wavelength of semiconductors. And they differ in size because at the metal, the Fermi energy, the Fermi wave vector Kf is quite large. So you wouldn't be expected to answer that because we haven't really discussed it. Here, write down a general expression for the electron density in terms of the density states and the Fermi-Dirac distribution for a one-dimensional carbon nanotube. Okay? We didn't do one-dimensional density of states, so I can't really ask you that exactly. That would be a little bit unfair. Yes? You did use what? Sorry, a one-dimensional? A 2D, yes. Yeah. You could be. Assignments are yes, available to be tested on. Yeah, but I don't think we did 1D. But we certainly did. Okay, we certainly did 3D. So yeah, you should know it for 3D. And okay, good point, 2D as well. What else? Oh, okay, here we are talking about some array of phosphorine atoms. We didn't really talk about phosphorine atoms like on the surface. I don't even know if they are metallic or semiconducting. So yeah, you won't need to know that one at all. And this one here talks about the melting temperature, the correlation of the melting temperature and the coefficients of thermal expansion. Now, I'm not going to ask that one because we didn't talk about thermal expansion coefficients. Okay, so cross on that one. And yeah, what I want to say, all of the exams and the current one too will have the same format. There will be 2 questions for all students, and then there'll be 1 question for normal and 1 question for advanced. So continuing on with the exam from 2014. Okay, band structure using the nearly free electron model and the tight binding model. Yes, you did that. That's fine. Here you are asked to derive an expression for the effective mass of the electrons at the Fermi level. Now, we didn't do an equation like that by approximating the conduction band as this sine squared thing. So I'm not going to ask like that because we didn't do it. That's not to say that you couldn't do it, because you will probably know the formula, or you will be able to see the formula for the effective mass. Remember, it's just 1 over, the effective mass is, okay, 1 over the effective mass is equal to 1 over the h bar squared. And remember, it's a second derivative of the energy with respect to k. So all you'd need to do is differentiate that twice and plug in the values that you've been given. But we didn't do it, so I'm not going to ask it. Okay, we talked about the Hall effect, yeah? So you'd be able to do that one. I mean, that could possibly be on it. And we talked about the temperature dependence of the resistivity. You could talk about that. Yes, you would know that. I wouldn't ask you about the T to the 5 variation of it, because we didn't discuss it. You recall that the curve sort of went like this. This is linear, and this is constant. In this region here, there is some T to the 5 behavior that goes on that we didn't discuss. Okay, normal only. I think I still go through it because one could still take a normal, and it could be on, you know, the first question or so. So we should go through it. Okay, Coulomb charging. When you see that, no, we didn't do it. You don't need to know it. You did do a question similar to this. You've seen one like an atom occupying a certain volume of space. You would be expected to know that. And this question where you can write about, it's a bit like a mini of your assignment part 2, where you did that 2-page discussion on a subject of your choice. I guess here is like a mini version of that. You could use the same one that you did in your assignment, or you could just talk about something else. Okay. Okay, so for the advanced, the question is, okay, let's just shoot here for the first thing. You can see that the advanced has a similar question. Okay, the same kind of question there, but for the advanced, you are expected to maybe give a little bit more. For example, how does that subject fit in today's world, and what are the open questions for research related to the topic you're talking about? So for the advanced, one would expect a little bit more depth. So what else? Okay, this is talking about again, the one-dimensional density states and ballistic electron transport. We didn't talk about ballistic transport. Don't worry about that. You will not be asked about that. Okay, we also didn't do superconducting. Okay, so superconductivity is probably going to be treated in 4th year now. So, okay, good. That was 2014. I guess we can keep going through them a little bit, if you like. Okay, here again we can see another question by Drude. Okay, it's talking about why it fails and so on. Yes, you know that. The Fermi energy of copper, you're given the Fermi energy of copper. What fractions of electrons are above the Fermi level? Yes, you have done a question like that, I believe. Write down an expression for the density of states. Okay, here we are. Now it's given in terms of the 2-dimensional material. So, okay, yeah, I forgot that. Thank you. If you, you should be able to do that one then for 2D if it was in, I've forgotten what's in your assignment. Yeah. Yeah, let's see. Electrical resistance here. Microscopic explanation of why materials expand. And how you might design a material with a... Okay, you won't be asked how to design a material about thermal expansion, because we didn't do the thermal expansion coefficient. However, you probably should be able to explain why most materials expand. Remember that potential well, and how as a function of the potential that an electron feels, and as you go further, the lattice spacing is further away. Remember, the potential is not harmonic. It sort of bends over, so at some thermal energy, the equilibrium lattice constant is slightly larger. So that one you should be fine with. Tight binding approach, yes, you did that. Should be able to do that. Okay, this question B, again, you'll notice is the same question, similar question, should I say, to the one that we discussed before. In the only difference here, you have to determine the effective mass again, but instead of treating the conduction band as a sine squared, yeah?
Maybe I'll let you finish.
Oh, okay. Okay. Yeah, and here they are just treating the valence band with a different equation here. I think valence band. Again, to determine the effective mass, you would differentiate this twice, okay, with E with respect to K, and use the values that you've given. But again, we didn't do that, so I can say that won't be on the exam.
Yeah. With regards to these sheets of paper, could you please upload them on Canvas?
I was going to ask at the end, would that be useful? Yeah, okay, I can do that. Yeah. Let me see here. Different atoms have different... Okay, again, here you can see a question about the Hall coefficient. Okay, some of these questions repeat if you look back over the years. You would know that one. Okay, here, again, they're talking about some Coulomb blockade. We didn't do it, don't need to know it. So on the second page, okay, here at the AIN, they're talking about the interaction of light with the optical phonons. We didn't really talk about the interaction of light with the optical phonons, so you don't need to know that one. Again, you can see some pattern coming here. You can write a little essay, a little mini discussion about your favorite topic. And as you know, it's not a complete list. You can choose, any topic that you like, really. Okay, what here we've got? This one you don't need to do again because it's to do with ballistic transport and one-dimension density of states. Should we go through them all or not? Okay, this is 2012. All of the first ones you could be expected to know. You can see it's about Drude, it's about the Fermi energy of copper. You can see it's about the expression for the electron density of states. Here they don't say if it's 1, 2, or 3. Here we are talking about the nearly free electron model. This is fine. Bullet mechanism leads to room temperature ferromagnetism. You talk about the exchange interaction, so on. The difference between metals, insulators, and semiconductors. Yes, that's something that we did. Again here, okay, it's called a Chili-Sherry atom. It doesn't matter what it's called. It's still an atom that occupies a volume. And, yeah, you should be able to answer that question without too much trouble. Okay, again, here we have the resistivity as a function of temperature. Again, you can see it's the same question. You would not need to know about the T to the 3 or T to the 5 relationship. I would more ask something, what explains the constant value of the resistivity as a function of time for low temperature, and why is it linear for high temperature? Because that's what we talked about. Okay, let's see what else they've got there. Provide a brief explanation of why most materials expand when heated. Okay, we've had that one before. Consider the phosphorus atom in a silicon. Yes, you should be able to do that one. Yeah, I think in the lecture we didn't call it the Bohr model, okay? But what we talked about was, remember when we had, say, a phosphor in a semiconductor, there's an extra electron, okay? And that extra electron and the hole left behind in the phosphorus atom behaved like a hydrogen atom, and there was this bonding between them. That's what it's talking about here. So, yes, you would know that one. and you go back in your notes, look like a bound state of a hydrogen atom, where it's very similar to the binding like we did in a hydrogen atom, except you have to take into account different dielectric constant for the material that you are in. And that enters in the expression for the binding energy. Again, choose a topic. Fine. Advanced only. This is obviously a no. Consider the thermal energy stored in a block of copper. Why do you need to calculate heat for making use of the Planck distribution? Anyway, no, that looks strange. We didn't really do that one. Okay, the band structure of silicon is that you are given the mobility of that based on the narrow band model. Okay, we didn't do the narrow band model, so you don't need to do that. We just treated it as an actual semiconductor. We didn't assume anything about the widths of the valence band and the conduction band. And again, choose a topic.
For question 7 to 7, did we do binding energy?
Which 7?
Question 7.
Question 7.
Minus.
Yeah, question 7. I think in the notes there was an expression for the binding energy. Yeah, if you look back on the slide, you should be able to see it. If you can't and you're worried, email me. Yeah. Okay, advanced only. Yes, we do not need to know that one. And this one here, yeah, sorry. Yeah. We didn't do the narrow band approximation. So 2011 still. Okay, you can see this is exactly the same question before about approximating the conduction band as this sine squared thing to determine the effective mass. Don't need to do that. We didn't do it. We didn't. This is again the interaction of light. We don't need to do that one. Or you would not be expected to know that one, I mean. Derive an expression for the conductivity when making use of the concept of the Fermi. No. No, I put a no there. Yeah, because I said, you don't need to derive an expression. We don't. This year we're not doing derivations. I could easily put in derivations, but I'm just telling you, no. Okay, this is all students 2011. Okay, again, it's how does the resistance or the resistivity vary as a function of temperature? You can see there is some repetition. Yeah, the questions repeat quite a little bit. So that's interesting. Phonon dispersion relation of germanium is shown below. Derive or the 4 branches in terms of the motion. No, we didn't discuss that. Hall coefficient, yes. There's another Hall coefficient. Explain the sign of the Hall coefficient. That's fine for you. Okay, again, we've got a new element called sydnium. Again, it occupies a certain volume and contributes 7 free electrons per atom. So calculate the value of the Fermi energy. You'll be able to do that one because from the information you're given, you'll be able to work out the electron concentration, N. And once you've got the electron concentration, you can use the formula in our notes to calculate the Fermi energy. Okay, you may not remember it offhand, but you can. Same thing in a little essay. An intrinsic semiconductor has a band gap of 3 doping levels. Okay, in this case you are given information about the position of a dopant level below the conduction band. Yeah, you don't need to know that. We didn't do that. Although we did lots of other things, right? So don't need to do that. This one you could easily do. Going back a little bit more, 2010, there's only 2 more to go. Nearly free electron model, yes, you will know how to do that one. This one here, again, you see the same question, the conduction band being approximated by the sine squared. Here we have a question about why is the conductivity differ by 30 orders of magnitude, yet the specific heat is very similar. We didn't discuss that directly, but it's to do with the fact that the electrons that contribute to the specific heat are only those near the Fermi level that can be excited above the Fermi level, and we did that, but we didn't discuss it in that kind of terminology. Explain the difference between metals and insulated semiconductors. Yes. Graphene is a 1 atom thick. Its band structure is such that the conduction bands meet at 0. Remember, graphene had this really interesting direct cones, and so you could tell here about some of its expected electrical properties. So you could probably say something about that. Okay, this again is a question about semiconductors where you're given a dopant level being introduced below the conduction band minimum, and you are asked some questions. We didn't do a question like that. And again, you see the same things. Advanced, looking at here, we're given the energy gap and assuming the wide band gap model. Now, we didn't talk about wide band gap model, so you don't need to know that. You'd probably get very worried if you saw that in an exam. What on earth is a wide band model? So you won't get that one. This one, of course, appears again. Has anybody already looked at these exams already? Not yet. Okay, well, you probably would have anyway, wouldn't you? I guess you would have. In your STUVAC, you would have gone over and looked at these, yeah? I'm just wondering, yeah. Okay, so this is 2019, 29. Again, you can see that same question there. Again, the same question here. Again, the same question here. And a similar question here. All should be fine. Okay, here is, yeah, we didn't do anything like that. Don't need to know how to do that one. This exam has fewer questions, actually. Your little essay, and here again they're talking about a wide band model. We didn't do that. You don't need to know that. Okay, I think this is the last one. You can see here, this is exactly the same question. Metals differ. This is exactly the same question. You don't need to. This is exactly the same question, and this is exactly the same question. Anyway, somebody was in a big rush, I think. Okay, this is the same question, and you don't need to know that one. And this is just write a topic. Okay. Okay, we've got one more. Okay, this is another wide band gap. This is the same. You don't need to know that one. Anyway, that's all I have for you. So, you know, obviously there were quite a few questions that you didn't need to know. Yeah? Yeah. That's a good question. I don't know. Yes, absolutely. I will find out. Yeah, and tell them to do it as soon as possible. Yeah, if we can get it done. Okay. Now, is there any other questions you want to ask now? Any other worries or anything? As I said before, you can always just email and, yeah, we will respond. Okay, yeah.
So you said the exam will be very similar to the
Yeah, in format style.
Will it be as similar to those exams as they all were to each other?
The thing is, you don't know what was on 15, 16, 17. Look, there will be some questions that are very similar. That's only fair, that there has to be a little bit of continuity. There might be some new ones introduced, obviously. Yeah. Okay. Yeah.
Was there a discussion question in the 2015, 16, 17?
When you mean a discussion question, what do you mean?
Like the give a report on superconductivity.
Oh, I don't know. It could be there's a high probability. I'm not going to say yes or no. That's all I can say. All right. Good luck with your exam.